Hey folks, we're finally getting into this kinetics thing. I'm awful excited. I love kinetics. It's what I do in my research, predominantly as an atmospheric chemist. You see a lot of atmospheric chemists that are into kinetics because it's all about thinking about how chemistry evolves in time. And as it turns out, that's a really interesting phenomenon for atmospheric environmental chemistry. How much time does this reaction take? Is it important to the time scales that we live on, and so forth? Okay. And so we're going to go through in this first section, this intro to kinetics, the basics, the fundamentals. All right. And then I hope we have enough time that I can really get into the interesting stuff, the techniques, the applications, and the advanced stuff. All right. So I'm just getting my make sure I had a timer going so I don't talk too long. All right. So let's get it going. So the first thing that I want to discuss is reaction rates. Okay. And so we're going to define the reaction rate. Let me get a thicker color there. There we go. So I'm going to say rate equals. Okay. And I'm going to first do this in terms of all of like the very correct physical chemistry terminologies, and then we'll put it into terms that we're more familiar with. Okay. So by definition, the rate of a reaction is 1 over the volume of the system times dz dt. And if you recall, this z thing that we calculated, right? That's called our extent of reaction, which by definition is going to be the number of moles of species J under final conditions, right? Minus the number of moles of species J initially, all divided by its stoichiometric coefficient. Okay, so it's basically how many moles have reacted, in addition to its correct stoichiometric ratio. Okay, so now I could write that as still write 1 over volume times 1 over the stoichiometric coefficient times the change in number of moles with respect to time. Okay, and of course we recognize that the number of moles of species J divided by its volume is just simply going to be its concentration in molarity. Okay, so the rate of any one individual reactant will always be 1 over its stoichiometric coefficient times the change in concentration with respect to time. Okay, and so this is for a homogeneous reaction in a constant volume container. All right. So let's see here. Okay. And so now in terms of units for rate, okay, so our units, there's going to be 2 main sets of units we see. One is more appropriate for solution phase, and the other is more appropriate for gas phase. All right. So units will be, we know that molarity, right, is mole per liter, and per unit time is per second. So that's going to be mole per liter per second. And so this is more appropriate for the solution phase, okay, or liquid phase reactants. All right. But the standard units for gas phase reactions, they're a little obscure. It's a little, what you wouldn't expect necessarily, but it's in molecules per cubic centimeter per second for gas phase. And there's several reasons for this, and I'm going to be getting into that as we go throughout this semester, or as we go throughout this section on kinetics. Okay, so molecule per cubic meter per second. All right. And so for this gas phase, okay, just to give you some familiarity with that unit, molecule per cubic centimeter, all right? So we know that we can calculate that by saying N over V equals P over RT. So I just kind of quickly rearranged the gas law, all right? And so we know that that would give me mole over liter. So if we do that for just normal room temperature, so let's say 1 atmosphere and 298 K, I got my handy calculator here, right? So I can say 1 divided by 0.08206, okay? And then divided by 298. So that gives me 0.0, I'll do 3 sig figs, 409 mole per liter, all right? And to get that into a molecule per cubic centimeter, we know that in 1 mole, there's an Avogadro's number, so 6.022 times 1023, all right? And we know in 1 liter, there's 1,000 cubic centimeters, okay? So now if I take this number times 6.022 E23, okay, and then divide by 1,000, there we go. That is one of my favorite numbers, okay? So that equals I ran out of room here. Let's see. So I'll write that over here, okay? So that equals 2.46 times 10 to the 19 molecules per cubic centimeter. So what does that number mean? That's the density, the molecular density of atmospheric pressure. So atmospheric pressure is 2.46 times 10 to the 19 molecules per cubic centimeter. You don't have to memorize that number unless you're like me and we use that number all the time. And so that's the number that I know, atmospheric pressure, 1019 molecule per cubic centimeter. But it's kind of a good off the top of your head when we're comparing like mole per liter per second to molecule per cubic centimeter per second. There's a lot of molecules per cubic centimeter, okay? So I just wanted to go through that just as a reminder, right, of how we do that, okay? So now what I've got here, this graph, as you can see, time versus concentration. So we can see a reactant decays. And so if we were doing this for the simple reaction, A goes to B, okay? I'll remind you that the stoichiometric coefficient of A equals -1, and the stoichiometric coefficient of B equals +1. So what that means in terms of the rate of these two things, we will see that A has a negative rate, okay? And so the slope at any one of these points, the negative slope, right, equals the rate because A is disappearing. And then B, in this very simple reaction that I did, right, just A goes to B, okay, we'll see that B, the product, has a positive rate, so it evolves in time. And the slope at any one point along this reaction is the rate. It is this rate in mole per liter per second in terms of the molar concentration, or gas phase molecule per cubic centimeter per second, okay? So now what about when we have stoichiometry? So this gets to our relative reaction rates, okay? And I'm just gonna draw up a simple generic example to talk about relative rates, and then I'll give you a real example, okay? So suppose we have the reaction A plus 2B goes to 3C plus D, okay? So if I were to follow through on that simple definition, right, it's 1 over the stoichiometric coefficient times dJ dt, all right? Then now what I can say is, if I start with D, okay, so D is just going to be d dt, okay? And it's 1 over 1 because there's a stoichiometric coefficient of 1 there. I'm not going to include the 1 over 1. So it's just dd dt, okay? I think that's what I said. So now in terms of C, I'm just going to write dc dt. And if I just follow this, right, 1 over the stoichiometric coefficient, it's just 1 over 3, okay? And then now in terms of B, we know that that stoichiometric coefficient is -2. So that means this is 1/2 dB dt, okay? And then A is just going to be -1/1, so I'll just say negative dA dt. And now these are all of the relative rates. These rates will all be equal now that I've considered the stoichiometric coefficients, okay? But if I don't consider the stoichiometric coefficients and I want to know, well, how will the rate of D depend on the rate of C, okay? Well, we would expect to see that C is produced 3 times more than D for any one given unit of time, okay? Or for example, 2 of B is consumed for every 1 of A. And so now if I'm making all these rates relative to each other, that's why it's 1 over the stoichiometric coefficient, because it puts them all at the same rate, okay? So here's one example. So here's the reaction. And I'm going to do lots of fundamental atmospheric chemistry examples. So we're going to see lots of things involving oxygen, ozone, NOx, so oxides of nitrogen. That's what you get your car smog checked for, is NO and NO2. Okay, so here's one example reaction, okay? And so if I were to look at a time profile, time versus concentration of this reaction, so lowercase t for time, uppercase T for temperature, because temperature is a state function, okay, then I would see the following, all right? So I recognize, so I'm just going to draw the rate of O2, okay? So let's do that in one color so we can see it, all right? So here is O2, okay? So now we recognize, hopefully we recognize, that NO will be consumed twice as fast as O2, okay? Again, if I wanted to set them relative to each other, it would be 1/2 NO equals O2. So that would give me my relative rate, but my absolute rate would actually show me that the slope for NO is twice as steep as it is for O2, okay? So I would actually see a slope. If I picked a point, let's say that point, my slope right there, my rate would be 2 times as steep as my rate for O2 because of that stoichiometry. And then correspondingly, what I would see for the product for NO2, it will have the same rate as NO because of the coefficient of 2, assuming that I can draw those things being equal. But of course, they will be opposite in sign, okay? So that's the manifestation of relative rates versus absolute rates. And of course, if I wanted to make, for this reaction, if I wanted to make all those rates relative to each other, then it would go -1/2 dNO dt equals -dO2 dt, which equals +1/2 dNO2 dt, okay? So for now, it's good to just practice with getting 1 over the stoichiometric coefficient. When we build up the rate laws, we'll see that if, let's say we were interested in NO, and I wanted to figure out how to deal with this too, as we shall see, what we end up doing is multiplying by -2, right? And that would cancel this 1/2, but whatever's on the other side of the equation gets multiplied by -2. Okay, we're going to see that when we put together a rate law. Okay, so moving forward. Okay, so rate laws and rate constants. All right. So as was pointed out here, when I have, so at any point along this reaction, the slope represents the rate. Okay. And maybe you remember from Chem 110, maybe not, we had this thing called the initial rate, which the initial rate would just be the rate initially, right? Okay. We have what would be called the average rate. And so the average rate would be if I looked over a much bigger range. So my average rate would be, let's say if I looked at this point all the way down to this point and just calculated, the change, the rise over the run, okay? That would give me the average rate. So if I looked at that over that would give me the average. And if I looked at this point, what's saying right here, that would give me the instantaneous rate. All the same, hopefully what you realize, what you're seeing is all of those rates would be different depending where we are at in the reaction, right? The initial rate would look much larger than perhaps this instantaneous rate at a later time in the reaction, okay? So that's why we use what's called a rate constant, which will have a constant value across the whole time series of the reaction, okay? So let's do an example, another generic example. A plus B goes to products. And what I want to say with rate laws, okay, it's all about the reactants, okay? We're going to have to start getting used to seeing that, all right? It's all about the reactants. And obviously we can still do the rates of the products, okay? But when we set up these rate laws, it's all about the reactants because those are what's easiest to measure, right? We have finite amounts of reactants at the start of a reaction, but more often than not, we have zero product at the start of a reaction. So it just becomes easier to monitor the rates of reactants, okay? So it's all about the reactants, all right? So we could start by saying that rate equals negative dA dt, which we recognize from the stoichiometry. B will have the same rate, okay? So that's all good. And so now the way I can make a rate law out of this thing, I'm just going to use the generic rate, knowing that I can either set this equation equal to negative dA dt or negative dB dt, because both are reactants. And what I do to set up this rate law, it's always going to be K times the reactants. So K times the concentration of A raised to some power that I'm going to talk about soon, times the concentration of B raised to some power. So this is how we always set up a generic rate law. So this gives me my rate law. And so if we had a third reactant, if it was an A plus B plus C, then I would also have a times the concentration of C raised to some power, okay? So K is the rate constant. And as we shall see, the rate constant has the same value throughout the entire reaction. So it's basically a proportionality constant for rate and concentration, okay? And then finally, those little superscripts that I put up there are what's called the reaction orders, okay? So that would be the reaction order of B, and that will be the reaction order of A. And this is the complicated thing of kinetics is in equilibrium, we often just look at the stoichiometry and we get what those coefficients should be. They are the stoichiometric coefficients. Reaction orders are not necessarily the stoichiometric coefficients, okay? As it turns out, they are the stoichiometric coefficients when you have an elementary or a fundamental step, okay? But if you don't know what the mechanism is, if you don't know what the fundamental elementary steps are, then you can't say that these reaction orders are equal to the stoichiometric coefficients, right? You have to do the experiment. So reaction orders are often determined experimentally. Okay? Now you can also determine reaction orders from a complex, detailed study of the mechanisms, which would be theoretical. So you could do a theoretical study of the mechanism and determine the reaction order. However, that's hard. That's really hard. So we often always determine reaction orders experimentally. And I think I have that. Oh, look, I have a whole slide that says reaction orders that I didn't even use. All that stuff I just said, put it in here. So reaction orders, let's just do that, are determined experimentally or with a detailed, and I'll put theoretical, examination of the mechanism. And we're eventually going to do that. We're going to be able to do that soon. Okay? But the way that we often start this determining reaction orders is by looking at experimental data. Okay? Why did I have so many slides for reaction orders? Okay, this is what I wanted to get to. Okay, doing the method of initial rates. Okay, so this is a very classic way of determining a reaction order. So not only the reaction order, but also determining the value of the rate constant. Okay. And you actually did this in Chem 110. If you took Chem 110 at HSU, you did this. This was the clock reaction using, you used yeast, and what else did you use? Peroxide disulfate as an oxidizing agent. Now I'm forgetting that whole reaction. But anyways, you did it in Chem 110. And so here's how that works, okay? So when we look at this reaction, 2I atoms plus argon makes I2 plus an argon atom, okay? And this is a rather obscure reaction, so let's not worry about that for the time being. I just want to use the data from this reaction. The first thing we would do is set up our generic rate law. And we would just say rate equals K times reactants, so times I raised to some power that we're going to try to figure out. I'll just use the letter X. And then times the other reactant times argon, and it's going to be raised to some power Y. And again, we have to use experimental data to figure out what those values are. And if you think about this now, we have one equation with two unknowns, which actually means we need as a minimum 3 experiments, okay? So we need to be able to, in 2 experiments, hold one value constant while we let the other value vary, and then flip that. So that gives us 3 experiments, and you're going to see that now, okay? And so the way that I can do this, the way I can start systematically figuring these out via this method of initial rates is by doing the following. So if I pick a set of data, so for example, I'm going to start with this first rate of reaction, okay? And I'm going to write that down. I'm going to say that's 3.48 times 10 to the minus 3, and that was molarity per second, okay? And so I recognize all of that equals K times concentration of iodine times concentration of argon, okay? So now for this reaction, so the way I set up this table, okay, this rate resulted when we had, let's see, 2 times 10 to the minus 5th of iodine here, and 1 times 10 to the 3rd of argon. So that's how my table works, all right? So this rate is involved when argon stays the same, but now when the iodide is cut in half. So now I'm just going to plug in those values. So I'm going to plug in, let's see here, 2.0 times 10 to the 5th, that's molarity, and it's raised to some power. And then I'm going to plug in the argon, which is down there, 1.0 times 10 to the minus 3rd molarity, Y. And now what I'm going to do is divide this whole equation by another set of data, okay? And the set of data that I'm going to pick is I'm going to hold one of these constants. So let's hold the argon constant. And when I hold the argon constant, I have to vary the iodide. So that gives me to this experiment right here. Okay. So now that's 8.70 times 10 to the minus 4 molarity per second. And that equals K. And now my iodide is 1.0 times 10 minus 5th molar. Okay. And now my argon remained the same, 1.0 times 10 to the minus 3rd molar times Y. And so now the way this works, okay, K and K cancel. Let's see here. So 3.48 divided by 0.870. So I just dropped the exponents there. And you should work this out on your own for sure as well. So that all equals 4. Okay. K was canceled. But you can see now 2 times 10 minus 5 divided by 1 times 10 to the 5, all raised to the x power, is just going to be 2 to the x power. And now 1 times 10 minus 3 to the y divided by 1 times 10 to the minus 3 divided to the power y. That all cancels. So as you can see, this is a perfect experiment. So x equals exactly 2. In a real experiment, you know, your rates might not come out to like a real nice rounded number, but reaction orders are whole number integers, okay? Reaction orders are whole number integers. So that means we know that the order of iodide is 2. And we're going to talk about what that means in a moment, okay? Now when I want to go to do the next one, so I've got to figure out why. And so now I need to look at data in which the iodide concentration remains the same, but now the argon concentration varies. Okay, and so here's the one I picked. I'm going to do that 8.69 times 10 minus 3 molar per second, okay, equals K. And so this one resulted when I have this concentration of iodide and this concentration of argon. So now that's 1.0 times 10 minus 5. But I already know that that's raised to the second power for the second order because I figured it out up there. Okay. And then now the argon is 1.0 times 10 minus 3 molar raised to the y power. And now I'm going to divide that one by this 4.35 experiment. Okay. 4.35 times 10 minus 3 molar per second equals K. And you can see now why we do this systematic variance, because now I can knock out iodide from the equation. All right. And now, oh, you know what? That says 10 times 10 to the minus 3. Haha. Maybe you caught that. Maybe you didn't, but I just caught that. This is 10 point times 10 minus 3. And now this one is 5.0 times 10 minus 3 molar, all raised to the y power. And I can definitely do this one in my head. 8.69 divided by 4.35 is 2. Okay? And the k's and the k's cancel. And this cancels. And then now what I'm left with is 10 divided by 5 raised to the y power, which is just 2 to the y power. So y has to be 1. So what does all of this mean now? Well, what this means now, my rate law equals K times iodide to the second power times argon to the first power. So what we would say is the reaction is second order in I, it's first order in argon, and it's third order overall. So let's write that actually where I left all these blanks here. So if we had a reaction that looks like this, right, that data that we just did, okay, we would say it's second order in I. We would say it's first order in argon, and 1 plus 2 is 3, so we would say it's third order overall. And we're going to see the consequences of this in the next video. All right? So let's see here. Or like another one, let me just back up. Now I think I know why I had all this other stuff. So to give you another example, if I just said now, so let's suppose that a rate equals K times A times B. So let's suppose it worked out like that. And when I don't write a number on the exponent right there, it's implied that it's raised to the first power, right? So if I had one that looks like this, it would be first order in A, first order in B, and second order overall. Okay, so they all add up. All right, great. So that's 30 minutes. To me, that's a pretty good amount of time for this first video. So in the next video, I'm just going to be going one by one through what is a first order reaction, and then what is a second order reaction. So those are the main two that we're just going to stick with for this initial section. But then eventually we're going to start looking at the weird ones. Like we're actually going to see examples when there's half order reactions. So more often than not, these reaction orders are whole number integers. But of course, because chemistry is the science of exceptions, there are some exceptions to that when we get these weird half order reactions. And we're also going to talk eventually about a zero order reaction. Okay? So we'll get there eventually, but for now, for this intro chapter, we're just going to stick with first order reactions and second order reactions and what those look like. Okay, folks, I'll see you in the next one.